types together. So we could have written our functions this way instead, right? So in the first case, we'd be writing a definition that looked like fx, y equals something. And in the second case, we'd be writing something where we had the comparison argument, but we can get the same parts, right? Because we just can use pattern matching and get the two components of the pair. And then on the right, we write the same stuff. So those two things are, in a sense, equivalent, right? We are still writing functions that are essentially two arguments. Given an x and a y, you can compute the result. In one case, you just give the x and the y directly, strung out after the function name. In the other case, you have to package them up as a pair and give it a function, but it just pulls it apart as the first step and then does what the other one does. All right. So that's really one of the main points of today's class, is to look at this correspondence here between these functions that are written out in the first style and then the ones that work on pairs. And one thing that may not be obvious, well, we certainly haven't, I'm pretty sure we haven't mentioned it, is, we've strung out these three operators, or these arrows here, but what does that actually mean? Normally, arrow looks like a binary operator. Usually there's some kind of operator precedence. Right? So if you have x plus 1 plus 2 plus 3, that actually is just a nice way of saying that, or a shorthand way of saying it's 1 plus 2, then plus 3, or 1 plus 2 plus 3. And it works out okay for plus because plus is associative. Those two things, however you group them, then you get the same result. But nevertheless, plus is just something which takes two arguments. So what is the corresponding thing here? How would you break this down? Or how would you actually write this using in a fully parenthesized form? We indicate what arrows being applied to first and then second. And in fact, the way that you do it, what this actually means when Haskell parses this is this. Okay, and this is not the way we've been thinking of our functions, right? We think of two arguments here. This looks like a function of one argument now. But these two things, I should write them this way, they're actually completely equivalent. One is just a short way of writing the other. And this kind of reflects this distinction that we made in the first part up here. You can view it as taking a pair, or you can view it as these arguments strung out, but then, what does it mean to apply the function to just one of those arguments, which is highly suggested by this format here, right? We could, think of this as being a loop here, f of x, and then you take that and you apply it to y. Right? So that's what I want to get at today. How do we understand these function types as being something that looks like that? In other words, anytime you define a two-argument function in Haskell using the way that we've been doing it, what you're actually doing is defining a function which takes an argument and then returns another function which takes an argument and then gives you a result. So that's really the essential concept here. And as I said, it's not, we'll see a number of different ways of looking at this, but this really is the core idea, and the thing which is unfamiliar is how you actually incorporate that into your programming style. And if you started the coming assignment, you may have recognized or seen a need for something exactly like this, because we've written a lot of, well, if you've done it, you'll see that you're writing map and filter a lot, and they always take function arguments. And what's the function argument? Well, what's supposed to be. It's supposed to take one or two arguments and do this with it. But often what you'll see is that you write this lambda x and then some stuff, and you'll see that that stuff is sometimes just applying one function to maybe one argument. Like if you want to add 1 to everything in the list, you would do you map lambda I plus 1 over the list. So that's really taking the +1 function and mapping it over the list, but you have no way of saying the +1 function right now. You have to write this lambda saying, look, I have to input this, then I add 1 to that input, and that's my function. But wouldn't it be nice if you could avoid a lot of these lambdas just by using these partial applications, I'll call them. Like just, if you could just write something like +1 as a function, and that's what you map over something. So that can save a lot of clutter in your program, and it's a slightly different way of thinking about the functions too. You're thinking about these partial applications instead of always having a function with the full number of arguments spelled out. Okay, so that's a big part of today, and I just wanted to summarize the previous lecture. I can actually do it in one simple example here. Suppose you want to take a list. So double is Haskell's way of doing floats, which is double precision in floating point numbers. Actually, this will be mine. I just want to make sure that my recording is working here. Oh yeah, okay, that looks good. Oh, I can even see that the microphone is working. All right. Right, so given a list of numbers, you want to take the square roots of them, but negative numbers don't have square roots, those are the real numbers. So you don't want to apply square root to negative numbers. So what makes sense here, what you might want is, well, just give me the square roots of the numbers that are non-negative and throw away the rest. So that's what the square roots function is supposed to do. And we can define it using map and filter like we discussed last time. So if it's often helpful to think of these things inside out. So the first thing we do here is take our given list of numbers and then filter it, just keeping the ones that are non-negative. So here we're having to use this function here which tells us whether some x is non-negative or not. And once we've got that list, then we can just go ahead and map the square root across it. They're all non-negative, square root will work. And for some realism here, if you apply it to this list here, you can see it's just getting rid of the last one and then getting the square roots, getting rid of 2 of them, the -1 and the -17, and then you're seeing the square root of 1 of 4 and 2.25. So we're going to look at, so that's kind of summarized what we were looking at last time, ways of using map and filter to put together programs which would be a little more cumbersome if you had to write them all directly using recursion. And you can think of it, this is why Python has map and filter as well. You could write this kind of thing in Python easily using loops, but it's a much nicer way, since you're dealing with lists so much, to have a compact way of saying these things. And there's operations like getting rid of things in the list, or just keeping certain things from a list and applying something to everything in a list. Those are so common that they have special functions for them, and they encourage that kind of style of programming, which is different than other languages don't encourage that as much. Some actually make it rather difficult. So one thing, we'll see a couple things. I've already mentioned some of these things briefly, but we'll look at them in a little more detail or some more examples, just so we can be sure about them and so you can be comfortable using them. So these 2 things here we've looked at before, but for now, just I just wanted to note that you can make this thing look a lot more compact, and once you're familiar with this style of doing things, easier to understand by using these 2 operations with this. So this dot here is function composition, just the kind of composition you're used to from your functions course in high school if you took that. Function f equals to g when applied to x is f applied to g of x, right? So function composition, filter, and here's where we're using this nice kind of partial application. We've got this greater than equal function, which you've always probably used, always with 2 arguments, 1 on each side, but you can give it 1 argument and that becomes another function. Okay, so this is really a function which, we're missing the left-hand side here. So what goes here? Well, that's this is a function and that's where the input goes. So given an input, you stick it in that part where the argument's missing and evaluate what you got. So this is just the function, which it does the same thing as this explicit lambda that we have up, in the previous example. And it just means, it's true if the input is greater than 0. And so this filter here, this expression filter of this partial application is the same as the filter one up there. And all we've done here is note that, well, square root of x, we're taking this big map thing, map, filter, and applying it to xs. So here you have this filter. If you think of this as being a partial application here, this filter applied to one argument, which is a lambda. That's a function which takes a list. We're applying that function to x's, and then we're taking the result of that and applying the map square root function if you want to think of this as a unit. So that just is the composition of the two things, the definition of composition. And that gives us this nicer way of writing it. And you can actually read it instead of going back to the definition of composition and what these partial applications mean. You can kind of read it directly too. So you just think of the input coming in from the right here. And the first thing it does is, well, we apply this filter to it. So we've got a list coming in, it filters out the non-negatives. Composition means now we pass it into map square root. So we're just mapping square root across everything. So you kind of think of like a Unix pipe in some ways as well. So it's kind of nice because now you're just thinking about these, square root operation as a sequencing of two operations. You're thinking of it at the operation level instead of at the argument level. You're not thinking what happens for each individual argument. Now you're just thinking about putting together two operations. And so that's a nice level of abstraction that works out well for lots of kinds of programs. And so a little aside here, I mentioned higher order a lot, but didn't actually define what that means. This is a term that comes up, it's a big deal in mathematical logic, but we don't give a crap about mathematical logic here, but I thought it'd be good just to see, for once in your life, what the definition of higher order actually means. Higher order just means orders bigger than 1, and what's the order of a function? Well, if you want to have, I should say up front, higher order, the way you've heard it explained maybe is, it's just a language is higher order, a programming language is higher order, if you can treat functions as pieces of data. Right? So a function, you can pass it around, take it as an argument, return it as a value of function, and it all works the way you expect. So some languages are not higher order. C you might think is higher order, but all you can do is pass around function pointers, and that's very different than passing around the functions. If the functions are at the top level, it's fine. You actually have a definition for them, but if the things that are defined inside some other function that have some context, maybe they use some variables in the surrounding program, C doesn't do those. It'll either break or give you some bogus answer if you try to refer to one of those contextual variables. So if you didn't understand, that's fine. If you use C, it might make some sense to you, but C, although it has function pointers, is not higher order. You can't reuse functions as data. You can use pointers to top-level objects. It's kind of an approximation, and that gets you a long way in practice as well. But we can give a formal definition of order. I'm not going to give the actual formal definition. I'm just going to give you what the definition would be for types involving integers. Just like one argument types. Right? So order 0 is just a constant function of no arguments. Order 1 means that, oh, did I screw up this up? Oh yeah, sorry, this is all screwed up. Okay, this is, sorry about that. I'll write it down, I think I can fix this fairly easily. So order 1 is just normal functions over integers. So, for example, a function which takes an integer and produces an integer. And then the order starts increasing when you start taking arguments that are functions. So this one here is actually, you'll just write it in here. This is 2, this is 3, that's 4. So each one of these orders is obtained by taking the previous one and making an argument type out of it. So you can see here that order 1 is regular functions. Order 2 are things which take order 1 things as arguments. So instead of just taking integers and arguments in order 2, now we're taking functions of integers. So that's order 2, second order if you like. And actually, there are a lot of, there's languages, I don't know if I call them programming languages, but there's logics and things that are in between logics and programming languages that focus on second order. So you might see that. Then order 3, you can see we've just taken, this type here. This one here is just the same as this type here. Order 3 is functions that take order 2 things as arguments. So take as an argument a function that takes a function as an argument. And then in order 4, similarly, you have something which takes as an argument a function which takes as an argument a function which takes as an function, and you can just iterate that. So in practice, if you're getting up to order 3 or 4, you're probably doing something wrong or convoluted. Order 2 is probably the limit of what you would do in practice. But that takes you a very long way, and essentially what you need to understand in order to use any of these orders is kind of similar. You still have the basic idea of these functions as objects getting passed around, taken as arguments. All right. So that's just an aside there. If you don't like it, you can swap it into your brain starting right now. This is reiterating the basic idea for today. You've got these 2 types, and they're the same in a sense. They're not the same in the sense that if you use one and try to use it when the other is required, you'll get a type checking error. But they work the same way. And in fact, there's you can map back and forth between them. Each thing in the type pairs of A, B to C has a corresponding thing in the second type and vice versa. It's kind of one-to-one correspondence that respects all the structure that you expect. And we call that isomorphic. We're not going to go into what that actually means technically. But isomorphic for us just means that there really is this tight correspondence between them. There's a one-to-one correspondence. In addition, it kind of works the way you expect. You would expect functions, I want to give them arguments and get a result, and you can do that with both representations. Right? So maybe that's another way of viewing that, is that these are both representations of the same thing, 2 argument functions. Maybe that's probably worth stating explicitly. So this is actually 2 representations of 2 argument functions. Okay. And I just applied the 2 different readings here. The first one, functions takes pairs as input, pair A, B as input, increases C, and the second version takes an A as input and then returns a function that takes the B as an input and gives you the C. All right, these 2 functions here, I'm defining them here, but they're actually built into Haskell. This is this basic operation. This is what you'll see if you look at the book. I gave a pointer to the relevant book chapter on the first slide. This notion of currying is a common phrase. It's not just the name of this function here. Currying just is this idea of taking a function that's defined over pairs and turning it into a function like what we've been using. It strings out 2 arguments and gives you a function, returning functions. Right? So the definitions are really straightforward. We've almost given them earlier. So curry actually takes 3 arguments here. If we're looking at this the same way we've been looking at our functions so far, when we write things like this, we think of this as being, what we're defining here is think of it as being a 3-argument function in our usual sense, right? So we have 3 arguments here. Put it in quotes. So one of the arguments is the function a arrow b arrow c, and then we'll take something in a, something in b, and giving you something in c. And the definition is straightforward. If I've got this function f, which takes pairs and gives me a result, and then I get my 2 arguments, x and y, how do I apply the f to it? Well, I just pair them up and give it to f. And then conversely, Curry does the inverse of that. So if I give a function, an f here, which is defined in our usual way, takes 2 arguments, how do I turn it into something that works on pairs? Well, uncurry f, x, y, so uncurry f is supposed to take a pair and give you a result. So if I give it a function that's of the type a arrow, b arrow, c, take a pair, what's the result? Well, I just get the argument, the 2 x and y out of the pair and feed them to the function f. So these 2 things, these 2 definitions here, these are really, these are kind of the key things here. But one thing that's important to notice is that you can give a different reading to these types. So what we've been doing so far, we just thought it was a 3-argument type. But you can also think of it, if you think of how this is parenthesized, how this is actually grouped, what this actually means is this. In fact, you can put parentheses around b arrow c as well. That is equivalent, and similarly, this is equivalent. So if I had written in this first case, maybe I should just make a separate point here about it. So I'll put a star here. You could rewrite this to make it clear the correspondence between the definition and the type that we've got. So we could rewrite the definition as Curry f, and just using our lambda, we're essentially moving the arguments over to the right-hand side. This is exactly the same thing as saying it's a function which takes an x and a y and returns f of x, y. So that means exactly the same thing, but now this makes it clear how it corresponds to the type, because what we've written here, this is something which has type a arrow, b arrow, c. You can argue x in a, y in b, you get something in c. And similarly, uncurried works the same way. You could view that as a function. If you want to view it as a partial application, in other words, what does uncurry of f do? Well, it's uncurry of f gives you a function which takes a pair x, y, and returns f of x, y. And that would be in this type here. So this is kind of abstract, I understand that. We're going to see some very concrete examples of this in a bit. And once you start using this kind of correspondence here, it'll become very familiar quickly, I think. Because all of the examples kind of go the same way. It's just getting used to this concept of having these partial applications, functions, returning functions. So if you like equational reasoning, and I'm sure most of you do, you can do something like this. So let's suppose we just have some arbitrary f, x, and y of the right types. Well, we can do some equational reasoning on what this expression means. Okay, so we're starting with this, and we're going to see what it's equal to just by applying the definition and the obvious rules about running Haskell programs, right? So uncurry of f applied to x and y, what does that do? Well, first of all, one thing that actually we haven't mentioned yet which is, okay, corresponding to this idea of there being an implicit grouping for types. Parentheses, A arrow B arrow C is A arrow B arrow C. The same thing applies to function applications to arguments. So let me make a note here that this part here is, the first step is because whenever you write anything, actually I'll use a different letter here so you don't get confused. H is a good function. So if I write H, apply to a couple of arguments, let's call them W and Z. So that's normally how we would apply a function to two arguments. But again, we've got, you can think this has got this binary operator application. We've got two uses of it here. There's H and W, apply an application, and there's W and Z. So which way, and here it makes a difference. This is not an associative operator. What does this actually mean? How does Haskell parse this? Which is the first application to get done? And what Haskell does, what the notation is there's implicit parentheses around here. So again, this is this concept of partial application coming up again. H applied to two arguments, W and Z. What it actually is first of all, we take H and we apply it to the first argument. That gives us a function. We take that function and apply it to the second argument and get the result. So presumably, H is defined the normal way. H W Z equals something, defined as you've been defining functions so far. So this is just, the first step here is just using the notation that's built into Haskell. Right, so we started with this curry on curry expression applied to two arguments. And that's the same thing as writing it out like this as the second line. So you want to do the, so the second line is just a prettier way of writing the first line. Get rid of some parentheses, because we have this convention that you always have the parentheses kind of moved to the left like this. All right, so now we've got something that we can, this line here, the second line, we've got something we can work with. Curry is something which takes three arguments, right? So the F, well, we've got a different F here. Should use a different letter perhaps, but curry takes a function, which is this, and two arguments, x and y, and then applies the function to the pair x, y. Right? So that's all that's done in this third step. Right? The function was on curry of F, so that's the F from the definition, and we're applying it to x, y. And again, just by notation, so this step here is just notation. It's the same, we're parenthesizing to the left, you can get rid of that parentheses because that's the default when you just write them out one after the other. So uncurry f, x, y means the same thing as the previous line. And now we've got uncurry applied to two arguments, and we can just use the definition. It says take the function part, which is f, and apply it to two arguments x, y, to get f of x, y. So in other words, what we've done is we've taken this function, put a box around it here, we've taken this function here, curry of uncurry of f, and we've done some just pure equational reasoning. So the application of that first function in a box to x and y is the same thing as f applied to x and y. Oops. Let's use the box around the wrong thing here. Just the f here. So in other words, we've shown that curry, uncurry f, and f are the same thing. They're the same thing because whenever you're applying the two arguments, you get the same result. You can do the same thing with uncurry. Exact same equational reasoning, same kinds of steps. I'm not going to do it. what you end up with is these two equations, that if you curry and uncurry something, you get the same thing, and similarly doing the operations in the reverse. Right? So that really is the definition of isomorphism. You have a functions back and forth. If you convert from one representation of a function to the other one, and then come back, you get the same thing again. And so you have this nice correspondence between the two types. And I said it's almost definition of isomorphism, because you also wanted to respect what you know about function applications. So there's a little more to it than that if you really wanted to prove some mathematical sense of isomorphism, but we don't care. Here's just two other ways of looking at it if you find them helpful. There's nothing precise about this, it's just a way of thinking about it. We often write functions in this map notation. This thing here means it maps to. It's just a different way of writing functions. So we have a function in A, pairs A, B, pairs C, for some types A, B, and C. And a typical thing, a function in that type would be something which takes a pair x, y, and gives you some z. And I've written these square bracket. This does not have a precise definition, right? I just wrote as a suggestive thing here. So the value, it's just supposed to say that the value of z depends on x and y. X and y. Okay. All right. So a function in a pair A, B, or A, if you want to think of A cross B, pairs A and B, to C looks like something which takes a pair and gives you a Z. Correspondingly, a function, if you want to, if the other representation is something which, given an x, produces a function which, given a y, gives you the zxy. You can write that in lambda notation too. If you wanted to write an explicit function in this type, you could write it as a lambda. You can use pattern matching with lambdas. I don't know if you know that. And by the way, I made a note here. I'm using lambda here for backslash. I do like lambdas. I spent a big chunk of my early life working with lambda calculus and similar things. But the main reason is that I'm using markdown, and if I put slashes in, it gets really screwed up. It's hard to escape them properly. Any of you use markdown? You know what markdown is? Well, we're learning. It's become a kind of standard for writing documentation programs. GitHub, all the readmes in GitHub are written in markdown. I love it. So a function A in A cross B arrow C, you would write it as something which takes a pair as an input, or you'd write it the same way as we've been doing for and string out the arguments. So lambda x, arrow, lambda y, and then the body. Okay. In both these cases, these two things would be the same, writing the same body. All right, so that's a lot of abstract views here. I want to look at an example using an association list. I'm assuming that everybody by now is familiar with association lists. We've been using them quite a bit. Representing a function is just a list of ordered pairs. It's what you do in 1805 and comes up in 1405. It's a very handy representation. Before we do that, I wanted to just make sure that everybody understands what this dollar sign is. I've used it a few times, had some questions about it. I just want to make sure everybody's on the, I think using this phrase, on the same page. The only point of this dollar sign, well, actually there is one other small point that we maybe don't care at this point. The main point, the reason why I'm introducing it is just to save writing parentheses. And it saves a ton of parentheses. Parentheses are annoying, right? You have to mash them, and then it looks ugly to go over different lines, and they're awful. Dollar gets rid of not all, but most of them. And the whole point is just the same as putting parentheses around. So if I write F, $sign, and a bunch of stuff, I can use any operators I want, infix. This will put the same thing as if I take in all that stuff and put parentheses around. Okay. So anytime you have F applied to something in parentheses, and there's nothing else following it, you've grouped everything after the function in one big parentheses blob, you can take off those parentheses and use the $sign instead. Right, here's just a really simple example. We've used this div function, right, integer division, here to divide x by y plus 4. So I put y plus 4 in parentheses. But I could have used a $sign instead. So these two things mean exactly the same thing. Oh yes, I was going to do that Haskell file now. That's actually a pretty small screen. You know what? I think I'm going to actually skip that example. Yeah. I'm nuking that example. And moving on to, the example is just trying to look at this correspondence between maps on pairs and maps on individual arguments giving returning functions in the context of association lists. So I think what I'm going to do is I'm just going to, the code's already written. I'm going to just leave it for you to look at. It's a useful thing to see. It's very concrete. And so the idea is if I have mappings represented as association lists, how does this correspondence look? Well, remember the mapping and association list, you just have a set of order pairs representing the mapping. The inputs are the first parts of the pairs, and the outputs are the second parts. In the case of a function, let's actually look at the two types here. So if we look at these, if we think about these two types here, this one and this one, in terms of association lists, what do those look like? The first one looks like a list of pairs where each of the first elements are pairs themselves. And so it tells you for each pair A, B, what the corresponding value of C is. The second one, though, looks a little more involved because what you have is, this is equivalent to this, right? If you want to represent that as an association list, well, maybe you can tell me what does it look like as an association list? What would be the structure of that list? I want to represent a mapping, an object in this type, A arrow, B arrow, C. How would I represent that as an association list? So these are one argument functions at the top level. It's something in this type is something that takes an A as an input and produces a function as the output. So association list, the first elements of the pairs are the domain of the function. So that's just A. So elements of A would be the first elements of the pairs. The second elements of the pairs would be these functions from B to C. And if we're representing functions association lists, that means that the values, the second parts of the pairs are all going to be association lists. Those association lists then would tell you for each B what the corresponding C is. But the key thing is that these association lists are in the second part of the pair, right? So you've already got, if you're looking at a particular pair, there's already a first element, so that tells you the A part. And now what you're doing is you have the list which tells you for any possible B you can get as a second argument what the corresponding value is. So that it's worth going through the details on that. Just, I think it will help firm up your understanding of this correspondence here, because it is very, very concrete. All right, so let's look at some actual applications of this. I mentioned at the beginning that it's really useful to have these partial applications. And in a nutshell, what these partial applications are is simply just taking a function and giving it one argument. You can give it two here, but the one is probably the main thing that we'll be looking at. So if you have a function f, taking two arguments, and some element in the type of the first argument, then you can apply that function to the first argument, and that gives you something in B arrow C. So the point here is that we've already kind of argued why, or explained why this is a thing, right? So we know that this type checks, it's an actual object. But the point here is to emphasize why this kind of thing is useful. Why would you ever want to have a partial application? I gave one example earlier, and I'm going to give a bunch more now. I wanted to explicitly say what these sections are. I don't know if I used the word section before, but that's just the idea of taking a binary operator and filling in an argument, leaving one with blank, that giving you a new function. So I think this example here kind of explains it. All the other ones are variants of this. I wrote less than 3 here, right? But you can put the missing argument can be on the other side as well, so we could have done 3 less than. So this is a function, if you'll just explain explicitly what these things do, right? So this is a function which takes an I and returns true if and only if I is less than 3. And then 2 is analogous. True only if 3 is less than 9. So really, just, you can think of just something which takes this argument, sticks it in the spot where something's missing, and gives you this result. Right. So if I take this less 3 thing here, map it across this list, well, if for each one, it takes the 2, says is 2 less than 3? Yes. Is 3 less than 3? No. 4 less than 3? No. So you get 2 false, false. And similarly, well, actually, did 3 less than? Okay. Applying 3 less than, it does an analogous thing. Is 3 less than 2? No. 3 less than 3? No. 3 less than 4? True. So this is just a, this is a simple predicate case, but you can also do this with functions which build stuff. So the first example is just testing stuff, now we're building stuff. Here's the same thing. This looks a little weird perhaps, but it's exactly the same thing, right? Here we, in this case here, we had use of less than with the missing second argument. Here we have the use of cons with the missing second argument. And so it just does the same thing. For each element here, it takes that list element as the missing argument and then does what you say. It takes x and conses it on to the front of each element of the list. Right? Giving you that result. All right, so is this pretty clear, this example? If you didn't follow some of the earlier stuff, it's too abstract. This example here, if you get this, then that's kind of key to a lot of the practical value of these partial applications. Are there any questions about this? Good time to ask. All right, we'll see a few more examples. So what if one question that may have come up in your mind is that, there seems to be some special status to the first argument here, right? I talked about f of x here. So if f takes 2 arguments, then f of x is some nice thing maybe you can make some use of and apply it as a first class function. But what if f of x isn't meaningful for you? What if you really wanted f of y of the second argument? So you want a function which, given a particular second argument, now takes possible first arguments and does its stuff. Okay? But it doesn't work out quite as well, right? Because If you just take f and apply it to something at one time, that is the first argument. How do you get the second argument in there? And there's two ways of doing it. It can sometimes it's appropriate, looks fine. Other times it can be better just to use a lambda. Lambdas let you just supply all the possible arguments and then write what the function should do in those arguments, and that gets rid of this consideration about argument order and that kind of stuff. But there's two ways of doing it. You don't need to, if you don't want to remember these, it's fine. I'm not going to require that you do functions coding a particular way, at least when it comes to this argument order issue. But let's just, as a simple example here, suppose you wanted to divide everything by 2. So divide x, y is just integer division, x divided by y. If I do div of 2, that's a function which takes things and divides 2 by them. That's not what we want. We want to divide by 2. So we want to fix the second argument at 2 and then take in possible first arguments and do the division. So there's two ways of doing that. Flip is one of them. And again, you may or may not want to use this. Sometimes you kind of obscure your code. That's a judgment call. If you want to think of this function type here as parenthesized, maybe it's a bit helpful. You can think of this flip as taking a function, a arrow, b arrow, c, and giving you a function, b arrow, a arrow, c. And it works for any possible type, a arrow, b arrow, c. And really the only choice for writing this is to just flip the arguments. Maybe it's just it's very easy to define. So flip. So you want to define what flip does on 3 possible arguments. So it takes a function f, and then we'll use y for the member of b, and x for the member of a. And what it's supposed to do is it's supposed to apply f to the arguments in the correct order. Right? So f is something of this first type, a, arrow, b, arrow, c. F has to have an a as its first argument and a y as its second argument. Right? So it's just exactly what you expect. Take f, apply it to arguments in the reverse order. And now we can just use flip directly, right? If you want to think of this as being grouped, remember the default grouping here, this is just a notation, is flip div applied to 2. Flip div, you can think of as the flip version, so div with its arguments reversed in order, and then we apply that to 2. So flip div is the one which takes one argument and another and divides the second one by the first one. And that's what we want. The first argument is 2 here. All right, so you apply that to 2, 4, 6, you get 1, 2, 3. There's also this trick with turning prefix operators into infix operators. So we looked at this once or twice, I think. And again, it's not something that you need to burn into memory, but it is quite a handy bit of notation to use. If we wanted to, say we're writing div x, y, that's equivalent. You know, this is just a definition of what this backquote div notation means. It is exactly the same as writing div x, y. Okay, so you can take an ordinary function applied to arguments, and you can turn it into a nice infix function by putting backticks around it. Yep.
For flip div, is this supposed to be a 2, 1, 3? Not 1, 2, 3?
1.
Doesn't the b go to the first spot and then the a goes to the second spot?
Well, this flip div is, yeah, this is just something that's happening on the function part. The function still gets applied to each argument individually. And so if you look at the first application, you're applying flip div 2 to 2. Right? So that's, well, that's not interesting because they're the same number, but let's look at the second one. Flip div 2 applied to 4. Right? So if you want to substituting here. You've got flip, you've got div, and you've got two. You're applying it to 2 and 4, right? The 2's from the first part of the map, and then 4 is the list element, right? And that just says apply. So this is 2, that's 4, and that's the div. And it says, well, that's the same thing as div applied to 4, 2. So you're dividing 4 by 2. I personally find flip a little hard to think about, and I actually don't use it very much.
So what is flip supposed to do? I
Huh?
know that what's flip supposed to do?
It's just supposed to take a function and turn it into a new function which takes the arguments in the reverse order.
Then why is this in reverse order? That means 3, 2, 1?
Well, because it's not affecting the order that you apply to the list. It's just the function. So we've taken a when you map something, it has to be one argument function, right? And we've taken a 2-argument function and turned it into a 1-argument function. But whatever that function is, it gets applied to each element of the list. So there's no way of putting something in the function part of the map that's going to change the order of the list. It just gets applied to each individual member in turn. All right. Any other questions about that? This is the other thing I mentioned at the beginning. Composition is also pretty handy. We looked at this at the beginning. I'm not going to go through it again. Maybe just to explain again what the composition part is. Composition is just another function. I should write out an explicit definition of it here. So if you want to give a definition in our conventional style, this composition is actually something that starts out as an infix operator. You can write, function dot something. You put parentheses around it, it becomes a normal function where you put the arguments afterwards. And that's how we'll define it here, just so it looks like I want a conventional definition. So what does this do? It takes 3 arguments, right? F, takes an F, and a G, and an X. So this is, F is in this type, G is in that type, and X is in that type. And you don't have many choices here what to do because you have to end up with a C. How are you going to get a C? Well, the only thing that gives you a C is F. It needs a B. How are you going to get a B? Well, G is the only thing that gives B's. And what about an A? Well, you've got an A, that's X. So if I take X and I apply G to it, now I've got my element of B, now I can apply F to that. So that's dysfunctional. And we can write FG, that is entirely equivalent to F dot G. You have to be a little careful with using this composition infix style because you have to worry about parentheses. If I want to apply the composition to something, I need to put parentheses around it. If I don't, if I just wrote this, well, application is the tightest binding of any of the syntax operators. So what this means by tightest binding, I mean, where you put the parentheses, if you're totally parenthesizing, and they would go that way. That's maybe not what you meant. Using compositions then may require some parentheses. Okay. So this is an interesting example, or maybe not interesting, but it's a useful example because it brings together all the stuff that we've been looking at so far. And so here we have, this is a partial application. And Maybe we should put just to emphasize here that this is the way it gets parsed. And this is also a partial application, right, because filter. These are both partial applications. And here we have one of these sections. And then, of course, we have composition here. And as I mentioned, it's useful to think of this in terms of operations. An argument coming in on the right first gets passed through filter greater or equal to 0. So the list will get all the negative things you wrote. And then it gets passed through the map square root, which will apply square root to everything in the list. And the final result is the resulting list. So it's nice that we didn't have to, in a way that we didn't have to specify any arguments. We could have, but these two these are exactly the same, define exactly the same function. The same function is defined. It's really a matter of your own choice, which way you do it. I think it's very well worthwhile learning the second one. It's one of the values of the functional language like this is that it allows you to write programs in a more compact way. And whenever you can eliminate some kind of detail, it's generally a good thing. Sometimes it takes a little getting used to. So somebody doesn't know Haskell, they find a preferred way of writing it. Their preferred way is different than what than somebody who's experienced with Haskell would want. But in this version of square roots using composition, we are getting rid of one kind of concept. We're getting rid of the concept of an argument, explicit argument. So in a sense, it's a little more abstract as you can. All right, so this is okay. Well, so I want to look at a bunch of these. Did I write down? Oh yeah, there's a reference to the Haskell file. So I did want to look at some other examples, but before that, I thought it might be enlightening, perhaps, to look at this so-called law, because Haskell is amenable to equational reasoning. You can write down equations. You can actually have a bunch of laws about how things work, the same as you do in Boolean algebra. You have Morgan's laws. This is a representative of a big class of laws. This was maybe not so interesting, but they become more interesting for other kinds of data types. And it's important for doing program optimization. Is there any ideas why we would call this a fusion law? Anybody knows what data fusion is, and compilers or interpreters? So fusion refers to things being fused. So you have separate things which become one. And that's usually a good thing in compilers if you can get rid of some, if you have two things floating around, but somehow you can make them the same. It's called less space and less computation. So what are you fusing to what you're getting? It's kind of being optimized. It's not obvious. But what you have on the left, you have, imagine how this works. So on the left, you've got a list coming in, you map G across it, that gives you another list, and then you map F across that, that gives you a third list. But what about the right-hand side? You feed the list in, it goes across the list and then applies F composed with G, so each element applies G and then F. And that's the resulting list. So we skip that intermediate list. This just produces one new list by applying F and G at once to list elements. It's probably worth just a brief mention here. So you actually think about how this runs. It requires intermediate list. And this one doesn't. So the compiler actually looks for these kinds of things to optimize. If it sees expressions, map something, suppose it maps something, or things that can be turned into that, it turns it into the map with optimization. It saves a bunch of space. Okay. I'm going to leave it as an exercise then to actually prove this. And to prove it, you also prove in parentheses here, or quotes, just to make it not sound too odorous. But you can prove this just by doing the same kind of equational reasoning I did before, just applying the definitions. So what does map F dot map G mean? Well, the outermost operator is composition, so you apply the definition of composition, and then you'll end up applying the definitions of map. And if you want, you can do that the left-hand side, and then do that on the right-hand side, and end up with the same thing, or you can go from one to the other. But you just do a sequence of equational stuff where you end up going from one to the other. You piece together two things or not, doesn't matter. Okay, that's well worth doing, because I think it will help your understanding of composition and how it works in conjunction with the other operators you have in language. So even though you're proving something and you don't care about proofs really in the end, by doing that, it'll help you understand the kinds of, or see some of the patterns in your own programming that where you can use composition to make your programs more compact and readable. All right, so let's just look at some examples then. I think maybe if I just stop screen sharing here, all will be good. Oh, yes, it is. Okay. So let me. That look like it's going to be big enough? Terminal should be fine. Yeah, so let me delete this stuff. That's the stuff we skipped. It's all completed elsewhere. I'll give it to you on the website. So I wanted to define a few of these functions here, given a particular concrete context. Just because it shows, the example's chosen so it kind of shows how this way of writing functions can be quite compact and easy to read. We use composition and what else? Well, we'll see. A couple things which make this work well, and these are two things that are actually useful just for because they're more higher order constructs. This is something you'd probably never define in Python, although you probably could. This is just a version of AND. Actually, you know what? I'm not going to write a specification for it because the specification will look just like what we're going to implement. So let me just write down the definition here. So what this does is instead of, it's supposed to be like AND, but instead of taking just two booleans, now it takes, you can think of them as parameterized booleans. So it'll take two things which need an argument to give you a boolean. And when you get that argument, then you can feed the argument into both of them, get the booleans, and then do your AND. So it's really taking, normally the type would be bool, arrow, bool, and now we're kind of abstracting out an argument from each, from the result and the arguments. That's kind of vague, but let me just write it as probably the best. The definition is very simple. So let's suppose we have predicate 1, predicate 2, and then some particular input x, type A. Well, it's just P1 of x and P2 of x. So that's all there is to it. This really is and, just if you want to think of this kind of and lifted to Boolean valued functions instead of just being on the Booleans. So that's, you'll see why this is handy in a second. We can do the same thing with actually with if then else. Let me just get the type here. We're doing exactly the same thing with if then else. We're taking some element that's some type A, and we want to take all the parts of the if then else and now make them functions of this thing of something in A. So if you want to read the type of normal if then else would be, well, it would just be Boolean and then a B and a B and a B. But now we put an A arrow in front of everything. So what does that look like if pred, okay, so we have the test, let's just call it test here, and then true branch, false branch. And it's just a if then else, except now we just feed in the argument. So we've got an argument here. And given some x and a. Now we just do if then else, except now the parts have all needed arguments. We give them all the same argument. So here, test of x, then true branch x, else false branch x. Right? I wonder if that will actually be the file here. Let's do it. I saved it, right? Good. That code like I don't know. Just pump. That took a long time. All right. So those things are not really demonstrating higher order stuff. We're just setting up these examples. And I'm not sure I'll get through all of these. If I don't, then we'll just stop whenever time's up, and then the rest will be, I'll make sure that they're there so you can look at them. We're looking at this type of trees. Every tree has a key in it or some information, type A. And then the subtrees, before we're looking at trees that say a fixed number of subtrees, 2 subtrees, binary trees. Here you can have any number of subtrees. So subtrees, a node in a tree is just one of these bits of information, then as many subtrees, as many branches as you want. And the way of representing that is just a list of subtrees. Okay. So a tree is a bit of information and a list of subtrees. And as we are doing in the assignment, there's this notation. We looked at it in an example earlier too. If you write, if you only have one constructor, as we do here, a tree is only one kind of node. You don't have to have different, like a separate leaf or internal node. One kind of node, so we can actually tell Haskell to derive these destructors here, right? So info will be something. Actually, I'm just looking at the types here, just to be clear about what these things do. So what does info do? Given a tree, pulls up the information field. And what does subtrees do? Let's look at that. Subtrees. So given a tree, it gives you the list of subtrees. Right? So it just pulls up 2 parts of the tree. Something else, I don't know if you know, there's also this info thing. You know about info? It's useful for the built-in stuff. What's a built-in operation that we have here? Or we're using now, something that's used. Oops. So it's a handy thing. It tells you whatever it knows about the type and where it's defined. That's not a useful place to be defined. Data full list, what tells that? Okay, well, your mileage may vary. Okay. So the examples we're going to look at paths in the tree. The paths in the tree are just what you expect. If you want to give directions, starting at the root, how do you get to some particular node in it? You would just say which, as you go down, which subtree to pick. So at the top, you'll have some number of subtrees, and the way you pick the subtree to go to is by giving a number. So you have 10 subtrees, you give 7, go to the 7th subtree. And then the next thing in the path passes a list of numbers would be, maybe 5. And that means now you've got a list of subtrees again, go to the 5th one. All right, so just following, every time you get to a node, you get the next thing in the list and go to that numbered subtree. That's how you navigate through the tree. That's how you follow paths. There's a bunch of things you might want to implement for paths. For one thing, you might want to find out, check that a path is valid. So by valid means that you're always saying at any point go to the nth subtree. Well, there better be at least n subtrees. So just making sure a valid path is one where you're never going to go out of bounds. You're never going to ask for a subtree that's past the end of the list of subtrees. Right, so valid path, natural way to do this is recursion on the list of integers on the path. So if valid path empty, that's true. It's always a valid path. Valid paths. Now let's look at I. Okay, so we've got some non-empty path starts with I, and then I is the remainder. And what do we do here? So notice we're not getting the full argument list here. We're going to do this in a higher order style. So what we're actually doing is for each path that we might get, we're giving a function which takes a tree and then gives you the subtree, or gives you the subtree at that path. So it's the same thing, only we're just thinking of it a slightly different way. In each case here, we need to write a function. Okay, so this thing here is actually not a function, is it? Okay, so this needs to be something which takes a tree as an argument and gives you true value. So you're saying the empty path is valid for any possible tree, and we're returning a function that reflects that. So let's look at this handy function here, const. So that's exactly what we need here. So what does constant true do? Let's ask it to type that. Const true. So that's just a function which takes anything and returns the Boolean value, the true value. So on this side, we turn this into a function, we just return it into the constant function, which always returns true. Right? Now, in this case here, right, so we're doing, we can do a recursive call. That's probably going to be part of it. Valid path. Actually, let's not do that quite. Well, let's figure out what the recursive call would look like. So this is, right, so this is going to be our recursive call. What this is going to do is it's going to give us a function which tells us whether IS is a valid path for any given input tree. It seems like a little too general, right? Because we're saying, well, this recursive call is giving us a function that works on all possible trees, no matter how big they are. And yeah, it is, it's fine. The only reason, the reason this works is because we're doing recursion on this list of integers that's getting smaller. So the rest you can do anything with. Other arguments can become huge. All right, so let's try, I'm gonna try and finish this one example here before the class ends. Right, so when is the path valid? Well, the first thing I, that's an index into the subtrees. So that better be less than the length of of the number of subtrees. And then in addition, the remainder is needs to be valid for all of the subtrees. So we can also do it using this handy and pred thing. We can write that quite directly. So and pred. So in each case, we have two predicates which take a tree as an input. So what's the first thing? The first thing is we want to be I to index within the list of subtrees. So it can't be bigger than the length of the number of subtrees. So we can actually use one of those sections there. I less than and then opposed with length. Opposed with subtree. So I'll read this in a second. I'm just taking it out now. Okay, so that's one of the things. So when is this predicate true? Well, it's supposed to be. Let me put this in parentheses here. So we're composing three functions here. We're thinking and takes something which are functions, predicates over trees. So think of this composition of three functions as taking a tree input from the right. So we take a tree. First thing you see is subtrees. So that gets the subtrees out, a list of subtrees. And now we're taking the length of that list. And that's giving us a number. And now this thing is checking to see whether I is less than that number. So for any tree, this composite function here will tell us if I is less than the length of the subtrees of that tree. So that's one part. And the other part is that everything, all of the subtrees, IS is a valid path in those. And here we can just say, we actually want to say, I'll put this out in a second, I'll do this in a second. Let's take it out and then. So again, this is composition we should understand in the same way. So something which takes a tree as an input. So what's the first thing that happens? We get the subtrees out, and then we apply this function all valid path is. And what that says is that for everything in that list of subtrees we just got, valid path is of that thing. So list of trees, valid path is has to be true of every one of them. So for a tree T, valid is being true of that means valid path ist is true. So in other words, is is a valid path in that tree T. And all I haven't defined, but it's in the prelude. I just brought it in. So something which takes a predicate and tells you if that predicate is true of every member of the list. All right. So the next thing is there's no language here. There's no arguments. It's just a nice kind of sequencing of operations. And I can make the claim that once you understand this way of doing things, you're familiar with it, it allows you to understand program files a lot quicker than if I use explicit arguments. So I will fill in the rest of these